IIRS Dehradun. Today I'm going to talk about different Earth observation sensors and platforms. So before that, you have to understand the definition of remote sensing. So normally it is said that remote sensing is what? Collecting information without being in physical contact with it. So as per the definition here, remote sensing is the art, science, and technology of observing an object, scene, or phenomenon by instrument-based techniques. And remote means what? Because observation is done at a distance without physical contact with the object of interest. And sensing means detection of energy such as light or another form of electromagnetic. In simpler terms, you can understand like see the screen is visible to you. Why? Because the light is coming to me and it is reflected to the particular camera and that is recorded. So your sensor is recording the reflected energy. That energy is detected. So in that case, in our case, maybe the visible wavelength region is being used. So normally, even our eyes works also as a remote sensing sensor. So normally our eyes wavelength range capabilities are visible range only. So your remote sensing sensors, which are being used for airborne, spaceborne, or even ground-based platforms, normally they used the other wavelength range also other than your visible. So we can say that this remote sensing enables us to observe and study the nature in ways that would otherwise be beyond human capability because it will work in the infrared region also. It can work in the microwave wavelength region also, and it can take in measurement from a far distance. So first you have to understand the process of remote sensing. Normally what is there? There is sun from which the energy is coming and some energy is getting absorbed by the earth's surface. Some are getting transmitted and rest of the energy is reflected by the sun. Normally, the remote sensing sensors are of two categories, active and passive sensors. Passive sensors are those when the sun is the external energy source. But when the sensor itself is having own source of illumination, it is sending its own energy and backscattered energy is received back by the sensor. That is your active sensor. Now, normally what we assume that from sun energy should come and reflected energy should go to the sensor on board satellite or any platform. But it is not happening. What is happening in between that? There is an atmosphere. So because of the atmospheric attenuation, the energy we expect to come from the surface or from the sun is not same. So what we have to do that some errors are getting introduced. So those errors we have to correct, we have to rectify in the ground receiving and processing station. The errors, whatever is introduced, so it is recorded in the sensor, means as a data. Now it is converted to electronic signal, and as electronic signal, it is transmitted in the ground receiving station. So here I have used the term as ground receiving and processing station because ground receiving station is what? When the ground receiving antenna is in the range of the satellite, so it will transmit the data to the ground receiving antenna. And while converting, because it is receiving the electronic signal, we are converting the electronic signal in form of two-dimensional image. So the errors which gets introduced during the acquisition process, this needs to be fixed and then after it has to be given it to the user. So here you can see in this particular animation that how the satellite is coming with the range of antenna and the data is received in form of electronic signal. In case of our India, we have 4 ground receiving antennas at Sadnagar, Hyderabad, National Remote Sensing Center, Hyderabad. So now, but sometimes what is happening when the satellite is not in the range of ground receiving antenna and we require data on an urgent basis, then it is transmitting the data to some common communication satellite. And from that communication satellite, the data is transmitted to the ground receiver. Now the data which we will receive We can use it for various applications like land use, atmosphere, geology, hydrology, agriculture, forestry, disaster management, and so on. Now, the definition of remote sensing. So, as I told that our eyes also works as the remote sensing sensors. But that eyes have to be placed in a proper platform. Like our head is working as a platform where our eyes are placed to capture the data. Even whenever we are using our camera, what we are doing is we are properly putting it or in a stable way to take the photograph. So both sensor and platforms are used to create image data of Earth. Sensors are devices which records electromagnetic energy, and platforms are the carrier bed used to carry the sensor. Now let us go to the history of remote sensing, how remote sensing evolved. It started with the invention of the camera. So first photograph was taken in 1827. Then they started putting the camera on hot air balloon to take the photographs. And that balloon photography was used in American Civil War. Then after rocket cameras were patented, and then pigeon mounted camera in 1903 was patented. You can see here that how the cameras are mounted on the pigeon and the photographs taken from the pigeon are with wings. Then in 1906, photograph from kite was taken. Then 1914 to 45, when the aircraft, when that aeroplane was invented, then that was used during the World War One and Two. Then in 1956, U-2 spy plane was made. In 1957, Sputnik 1, that first satellite was made. Then first meteorological satellite was launched in 1960. But major involvement happened in remote sensing in 1967, when NASA launched a program that is the Earth Resource Technology Satellite Program, and that satellite was launched in 1970. But when they launched the series of satellite, they renamed that as Landsat. Now you can see this is the first photograph taken from the Landsat 1 satellite. Nowadays, we are using hot air balloon and kite photography also. But the limitation of these photographies are what? When there will be wind, they get little disturbed. So your photographs may appear little distorted because of the wind. Now, on the basis of the different types of platforms, means there are three main categories of the platform: ground-based, airborne, and space. So you can see here when spaceborne platforms are being used, what are the synoptic coverage for different platforms. With spaceborne platform of 800 kilometer, it is going to cover a very, very large area. With a platform altitude of 10 kilometer like normal aircraft, it is going to cover a little smaller area. Hot air balloon, nowadays UAV and drones are being used. With 100 meter, it can cover a smaller area. Then 10-meter altitude, like high-rise building or crane or something like that, can also be used for photography. And even we human can also stand and can go to the field for collection of ground truth data. So here you can see how the cranes are there where we can put the sensor and we can capture the data. This is the drone. This is the airborne platform and the satellite. Now, most commonly, we are using spaceborne platform because the data once you launch a satellite, it will continuously revolve around the Earth's surface and it will provide the data till its lifetime. Revisiting of the satellite will give you the data and again for the same. But in a case of airborne platform, whenever there is an urgency, we can fly the aircraft and we can capture the data. But the limitation of aircraft is what? We can process the data only when it lands. That is the first limitation. Second is what? Because we are flying once, for getting temporal data, flying again and again is not an economical option for the in place of your satellite. Then coming to your UAV, UAV is the cheaper version because you can fly an UAV and for a smaller area capturing of the data, UAV is one of the best optimum solutions. So here you can see ground-based platforms are normally used to record detailed information and it can be used for validation or calibration of the data collected from your aircraft or satellite. This can be used to better characterize the target which is being imaged by other sensors and making it possible to better understand the information. So here better characterization of the target means what? Like for example, suppose we have taken the data for some agriculture field. Now, how do I know that this agriculture field is having which kind of crop? So to know about the crop, we have to have some ground information. Then those sensors normally may be placed on a ladder, scaffolding, tall building, crane, etc. Now coming to the airborne platform. So as I told, stable wing aircrafts, helicopters, nowadays drone are being used as an airborne platform and to collect very detailed images and facilitate the collection of data over any portion of the Earth. So because of the lower altitude data acquisition, the spatial resolution of the data is quite better compared to your spaceborne platform state. Now coming to spaceborne platform. Normally spaceborne platforms are categorized into two, space shuttle and satellites. Satellites are more commonly used. Space shuttle is something like manned spacecraft where man can go to space and can come back after collection of data. Satellites are objects which revolve around another object, in this case the Earth. Now the satellite name, how it came into picture. When Kepler was observing the moon and Kepler was observing the Jupiter planet, what he found that four moons which are revolving around the Jupiter planet, it was appearing like some object, something is guarding that planet. So in his language, the word guardian, the other name of guardian is called as satellite. So moon, in our case, moon is considered as natural satellite in Earth's case. And whereas man-made satellites include those platforms launched for remote sensing, communication, and telemetry. So this is your how the spacecraft looks like, space shuttle, and this is the satellites, different satellites which are observing the Earth. Now, now you have to understand about the orbit and how the satellite is revolving around the Earth's surface. So normally the path followed by satellite is called as orbit, and the satellite moves as per Kepler. So first law is what? The path followed by each planet is an ellipse with sun as one of the focus. Second law is the line joining to the planet to sun sweeps out equal areas in equal time. So here you can see this is the elliptical path. Now in the case of our satellite which are observing Earth, so when eccentricity becomes zero, it may be your circle. So circular orbit is also there, which is one case of ellipse. Second law is line joining to the planet to sun sweeps out equal area in equal time. So here suppose this is A1, this is your A2. If it is taking T1 time, it is taking T2 time. So this is going to be constant. Then the square of the period of the planet is proportional to the cube of semi-major axis. Means if suppose it will take time t to complete one orbital revolution, so square of that time period is proportional to the cube of semi-major axis. Now you have to understand normally for different satellite, the referencing scheme is different. It is unique for each satellite mission. Normally what happens is the orbital path first you have to understand. Normally whatever data acquisition is happening, they are happening on a continuous basis. Now what we have to do is we have to divide our particular path, that particular data acquired in certain scenes or frames. So the path is what? An orbit is the course of motion taken by the satellite in space, and ground trace of the orbit is called as path. So this is suppose path. Rho is the line joining the corresponding scene center of different paths are parallel to the equator. So suppose this is my path, which is for the satellite, and this is suppose equator. So what we can do, we can draw parallel line to the equator to divide our different paths. So this is your path number, and this is your row number. Now suppose for example, Dehradun is existing somewhere here, and we have to order the data of Dehradun. So which path number and row number will be required, data of which path number and row number will be required, we can see through this. Now this is just a hypothetical situation. Suppose this area is Dehradun. In this case, path number 3 and 4 and row number 2 will be required for acquiring the data of this. So here, this is just an example of the image. You can see how the path number and row number will be defined. This is the path number and these are the different rows. And when you will see the data, your data will appear like this in your data browsing website. Now coming to the satellite orbital characteristic. So first you have to understand about altitude. So height of the platform from mean sea level of your Earth surface is the altitude. Inclination angle here is, suppose this is the orbital angle where the satellite is orbiting, and this is the equatorial plane. So the angle between this orbital plane and equatorial plane is inclination. Now this is important because sometimes what is happening when the satellite angle is orbital angle is 60 degree. So it will acquire data till plus 60 degree latitude and minus 60 degree latitude. So what about for remaining portion? So for remaining portion acquisition, we require inclination angle of satellite is as such that it can cover entire. So that should be near to the pole. Period is time taken to complete one orbital revolution of the satellite covering the entire Earth. Means suppose this is your Earth and time taken to complete one orbital revolution is called as period. Repeat cycle is like suppose this is Earth and satellite is revolving from North Pole to South Pole. Earth is continuously rotating from west to east. The same orbital path done by your satellite is called as repeat cycle. Means revisiting we are doing by making the same orbital coverage. Swath is the width, the area which is being seen by your satellite, that is called as swath. And ascending path and descending path. Suppose this is your Earth from North Pole to South Pole when Earth satellite is moving, that is called as descending path. And from South Pole to North Pole when satellite is moving, that is called as ascending path. Normally, this is important because if the sensor is passive, sun is looking to the Earth surface. So while doing the descending path, while moving from North Pole to South Pole, the data acquisition takes place for your passive sensor. But your active sensor can work in both the cases, ascending and descending, because it is having own source of illumination. Now coming to another term, perigee and apogee. Perigee is the closest point of your particular satellite to your Earth surface. Apogee is the satellite's position, how means the farthest point of the satellite from your Earth surface. So here, on the basis of that, as I told, altitude is height from the height of the satellite or height of the platform from mean sea level of Earth surface. So on the basis of that, there are three categories of your altitude: low Earth orbit, near Earth orbit, and geostation. Low Earth orbit, which is from 150 to 300 kilometers. So most of your spy satellites or space shuttle are using this altitude. Near Earth orbit, like altitude from 300 to 6,400 kilometers, most satellites for Earth observation. Geostationary, the altitude is 36,000 kilometers above the equator, which view 45% of the Earth's surface, equal geometry for each image. Inclination angle, angle between orbital plane and equator, this I already told. So to cover the entire Earth, we require pole around. Period and repeat cycle I already explained. Now, one term here, it is written as revisit time. So, revisit you can do by two ways. One, by making the same orbital path. Second, we can even control from here the tilt of your sensors, which are on board satellite. So we can, while suppose since satellite is moving like this, we have tilted the sensor and can see the same. So time between the two subsequent images of the same area is called as revisit. So on the basis of that orbit, your satellite is categorized mostly into two major categories: geostationary and sun synchronous. So geostationary, why it is called as geostationary? Because it appears to stationary with your Earth surface. Like this is your Earth. Satellite is at such position that whenever its Earth is rotating, it is moving with such speed that it is always going to continuously look to the same way. It appears to be stationary with respect to your Earth surface. So normally altitude for the geostationary satellites are around 36,000 kilometers. Orbit inclination is around 0 degrees. Period of orbit is around 24 hours. And global coverage requires several geostationary satellites. How? Because geostationary satellite position is fixed, it is going to see a certain portion of your Earth surface. So to cover the other position of the Earth surface, like you can see in this animation, this is going to see this area. So to cover the other position of your Earth, we have to launch several other geostationary satellites. This is good for repetitive observation, but poor for spatially detailed data. Now, because of the height, whenever I talk about spatial resolution, you will learn that height is one of the factors which is playing a role for the spatial resolution. Larger distortions at high latitudes means what? Your Earth's surface is not flat, it is curved. So whenever the data acquisition is taking place, the Earth curvature is also coming into play. So that's why the distortions are included at higher latitude. All the satellites, because Earth is also rotating from west to east, so satellite is also revolving from west to east. Mainly used for the communication, meteorological, and telemetry purposes. Both Meteosat, INSAT, and GSAT series satellites are for this application. Now coming to the sun synchronous satellite. The other name of sun synchronous satellites are near polar, near circular, and why it is called as sun synchronous? Because as I told that your satellite requires sun energy. So sun is fixed at that position while satellite is moving from north to south pole, it is capturing the ray. So that's why it is called as sun synchronous. And altitude is 700 to 800 kilometer. It is just an example of some satellite. For various satellites, there are different altitude, but the range is, as I told to you in my previous slide, that it may vary from 300 to 6400. Orbit inclination is 98.7 degree, which is near to the pole. Orbital period is 90 minutes. And the satellite orbit is fixed in space, like here you can see, and the Earth rotates beneath it. So because of this revolution of satellite and rotation of your Earth, whole Earth data gets increased. And normally, the satellite is moving from North Pole to South Pole and it passes the equator during the morning time. In this example, 10:30 a.m. is written. So during morning time, it crosses the equator. So that's why it is written as satellite orbital plane is near polar and the altitude is such that the satellite passes each place at same local sun. Example of these satellites are your Landsat, Spot, Sentinel, in and remote sensing satellite. So as I told that because of the rotation of Earth and revolution of satellite, so after completion of one cycle of orbits, whole Earth data gets in. So you can see how this is acquiring the data and whole Earth data will be. So as I told about, there are two major categories of remote sensing sensors, passive and active sensor. Passive sensors are what? When sun is used as external energy source and reflected energy is received back by the sensor. And in case of active sensor, it is having own source of illumination and backscattered energy is received by the sensor. Now, one of the in passive sensor, it works during only daytime. Active sensor can work both day and night time. But in case of passive sensor, one of the passive sensors like your thermal sensor can work both day and night. Because what is happening, sun's energy gets absorbed during daytime, it will emit at night time also. So that observation can be done using the thermal sensors. Now, on the basis of that imaging and non-imaging technology, your active and passive sensors are categorized. So imaging sensors are what? Which is giving two-dimensional image. Non-imaging sensors are your, you can say, profile device. So one of the instruments, spectroradiometer, is the device which is measuring the spectral reflectance curve. And active sensors are what? Laser distance meter, laser water depth meter, and microwave altimeter. Normally, these are used for measuring the distance. So laser distance meter is something like you are pointing a particular object with that instrument, and the pulse are get sent to the target. Two-way travel time is calculated, means that signal is striking to the target and received back to the sensor. So two-way travel time is calculated, and using that you can calculate the distance. So laser distance meter is used to calculate the distance. Laser water depth meter is used to calculate the depth of lakes and all. Microwave altimeter is used to calculate the ocean depth. Now coming to imaging sensors. So normal photographic cameras are imaging sensors, passive sensors. The optical scanners, like whatever satellite based sensors are there, multispectral scanners are there. So they are using two technology, across track and along track, for data acquisition. So I'll be telling you in detail in upcoming slide. Thermal scanner is one of the scanner which is receiving the emitted energy. And active sensors are your SAR sensor, which is working in the microwave wavelength region. LIDAR sensor are the sensors which are working in one of the infrared wave. So here you can see this is your one of the across track multispectral scanner. In this case, there what is happening, how the data acquisition is taking place. There is a rotating scan mirror and it is collecting data pixel by pixel, and your satellite is also moving in further direction. So here it is appearing like we are using a broom and we are sweeping the floor across the track and moving in further direction. So this scan the earth in a series of lines. You can see how this is acquiring, and lines are oriented perpendicular to the direction of motion, the sensor platform, and data are collected within an arc of 90 to 120 degrees. So here this P whatever is written, this is covering around 90 to 120 degree angle, that is called as field of view. This particular C is actually the instantaneous field of view, means whatever detector is there, it is going to make a solid cone, and that particular angle or that particular area instantly it is visualized by your detector. Normally, what happens is when we are using multispectral scanner for different wavelength band like blue, green, red, near infrared band, single detectors are there in case of wisp-room scanner for blue, single detector for green, single detector for red, and single detector for whatever number of bands are there. Means near infrared, short wave infrared. So for each band, there will be single. So multispectral scanner and thematic mapper and operational land imager of Landsat are using this particular technology. So now I'll be showing you one of the animation, how the wisp broom scanner is working and how it is collecting the data. But before that, you just see earlier they were using frame cameras for data acquisition. So one area at a go, it is collecting the data. So one frame, then another, it is collecting data like this. But when we have to acquire data, as using wisp broom scanner, it is collecting data pixel by pixel with the help of a rotating scan mirror. And as the satellite is moving, it is collecting the data. It is appearing like you are using a broom and sweeping the floor across the track and moving further. So you can see the particular time it is looking to the sensor, looking to the earth surface as the satellite is also moving. It is going to be little on the lower side. This term, the time by which the sensor, the detector is looking to the earth surface, that is called as dwell time. Now I'll be talking about the push broom sensor. So that is called as along track multispectral scanner. It is appearing in this case, we have thousands of CCDs placed in a linear array, and one linear array is collecting data by like we are pushing the broom and moving in further direction. So you can see this is thousands of detectors collecting the data and moving further, and this kind of image is getting captured. So this also scans the Earth in a series of lines. This uses the forward motion of the platform to record successive scan lines. And the particular detectors which are placed in the linear array, they are called as Charles coupled ripples. So examples of this are linear imaging self-scanning, wide field sensor of IRS series, and sensors of spot series are examples of this. Now, in this case, the dwell time is little long because at the same time when the satellite is moving, it is collecting the data. But in case of wisp room scanner, the rotating scan mirror have to collect pixel by pixel, but satellite is also moving. So the time up to which the detector is looking to the Earth's surface is little smaller in case of your wisp room scanner. So how to calculate that? So here you can see this is a cross track scanner where scan rate is 2 into 10 to the power minus 2 seconds per scan. In this line that is of 20 kilometers wide, the ground resolution cell is varying from 10 meter by means it is of 10 meter by 10 meter. So if we calculate how many cells are there, 20 into 1000 divided by 10, so around 2000 cells are there. So let us calculate the dwell time. Dwell time is equal to scan rate per line upon number of cells per line. So it is coming around 1 into 10 to the power minus 5 seconds per second. In case of push broom scanner, in this case, you can see the satellite is moving with the speed of 200 meter per second. Cell dimension is 10 meter per cell. When we calculate it, it is coming as 5 into 10 to the power minus 2 seconds per second. So if you have longer dwell time, it means you are allowing more energy to be received by sensor. The example you can compare with, like suppose you have taken a camera, you just take out camera, click the photograph. You will not get the proper information. Now take out the camera, put it properly, focus the feature, and then capture that. So it means you are allowing more energy to be collected by the camera. So same way here also we are doing by that, and that further is further used for generating high resolution. So normally for getting high resolution means how we are getting very high resolution satellite images from space. So in case of push broom scanner, we have linear array of detectors. Here we are using area array of detectors. It means we have n number of arrays placed one after another. Suppose this array has collected data, it passed it to the following array, then again it passed to the another following array, and whatever data sets signals have been received, they were integrated. So this technology is called as time delay integration. Here you can see that for first pixel, for first array, then second array and third array, and integrating it, you are getting better. Second high resolution imaging mode is step and stare. In that case, what is happening is like for the same area, you can see this is your start time, this is your end time. We are starting from this time and observing that particular object and moving at different steps and steering to the same place till its visibility and integrate the signal like is done in your time delay. So more the signal, better will be the resolution capability of the sensor. So now, normally what is digital image? If you zoom it, any digital image, you will see that a square shape feature will come. And we know whenever we are interpreting digital image or any display image also we are trying to keep, what we are doing little bit of enhancement, little bit of change in the brightness and contrast so that image appear more clearly for interpretation. So here how we are able to do that, because your data is nothing but some numbers are, and these digital numbers are seen by your computer. Now coming to the definition of resolution. So here you can see the size of the pixel will be termed as, means will give you a details about spatial resolution. The number present in that is talking about the radiometric resolution. And as it is a single band data, when you have multiple bands, then that will talk about spectral resolution. So here you can see the definition of resolution. Ability of a sensor to render the information at smallest discretely separable quantity in terms of distance, in terms of wavelength, in terms of time, and in terms of radiation. So spatial resolution is what? A measure of discernible physical dimension on surface from the. Spectral is what? A measure of the width of the wavelength which is used to generate the image. Narrower the bandwidth, higher the spectral resolution. And radiometric is what? A measure of what is the minimum change in radiance that can be measured. So I'll be telling you how it is going to be seen in the image. Temporal means what? How frequently we are revisiting the same area by viewing under the similar geometrical condition. So now coming to the spatial resolution. Normally, as I told, that spatial resolution is dependent on the instantaneous field of view and height of the planet. So here you can see this is your push broom scanner, and for single detector, the area observed over here is. So here when we zoomed it, in this case, this is your instantaneous field of view. This is your detector dimension A. This is your focal length. This is your height, and this is your x. So when we have to calculate IFOV is equal to A upon F and X upon H. So when you will multiply this IFOV with the height, you will be getting the ground resolution element or instantaneous ground field of view or ground resolution. So how it varies with the information content with the resolution. You can see this is the data, ocean color monitor data with 360 meter resolution. Here we have taken 4 kilometer by 4 kilometer area. With that 4 kilometer by 4 kilometer area, we are hardly able to see anything in the state. Now, when we took 188 meter resolution, the little better information is there, but not clear. When we have seen that 72 meter resolution data, the information is little better compared to your 188 meter resolution. Then this 36 meter resolution, here now we started observing a kind of airstrip, vegetation, urban feature, but still not clear. Now you can see this multispectral. In multispectral, the detailed features are visible, but the shape of the features are not that clear. But here in panchromatic, the shape of the features are. Now, if we have to compare multispectral and panchromatic, normally what happens is panchromatic sensors have better spatial resolution as the panchromatic sensor is using wide range of wavelength as a single band, like visible range or visible to near infrared. But in case of multispectral, those wavelength range is further subdivided into narrow channels, that is blue, green, red, and near infrared. Now here you can see the other example of the resolution. With 56 meter resolution, we are not able to see the features clearly. With ETM 30 meter, this is better than previous one, but not that clear. With LIS3 sensor, better than previous one. Then your ASTER 15 meter resolution data. Now we started observing the agriculture field, urban, and vegetation. Here you can see this is the IRIS 6 meter panchromatic data. The agriculture boundaries are clearly identified, but panchromatic is as it is a single band, so that's why it is appearing in grayscale. Then ICONOS multispectral data with 4 meter resolution. You can see the detailed feature discrimination present in this particular image. But here also the shape of the features are not that clear, but in case of panchromatic, this is comparatively better than your. So normally for what application we should use what data? For meteorological application, we should use 1 to 2 kilometer and 8 kilometer resolution data. For oceanographic application, like ocean color monitoring, 300 to 1100 meter. For land use mapping like crop monitoring, forest mapping, hydrology, 20 to 30 meter. Cartography and urban planning, 2 to 6 meter. military surveillance less than equals to 1 meter resolution data is available. Now coming to spectral resolution, this describes the ability of sensor to define fine wavelength intervals, and this refers to the number of bands in the spectrum which the instruments can take measure. So higher the spectral resolution, better ability to difference in the spectral signature. So how? As panchromatic is a single band data, all the features will appear in different gray color. But in multispectral, when you have more number of bands, you can generate color composite and you can provide different colors to the data. So the spectral reflectance curve will be better than your panchromatic. Now here you can see there are three data, two multispectral, one hyperspectral, with 6 band, 9 band, and 150. The spectral reflectance curve is in more details when we are using hyperspectral. So on the basis of spectral resolution, the data sets are categorized into three major categories: panchromatic, multispectral, and hyperspectral. Pan is a single band data, multispectral when you have tens of bands, hyperspectral when you have hundreds of bands. So now using the different bands, you can generate different color composites also. When you are using the same band, because there are three primary colors, red, green, and blue, and you are visualizing through red, green through green, and blue through blue, that is your true color or natural color. But when we are using near infrared through red, red through green, and green through blue, then that is called as standard false color composite. So these are the different bands and used for different application. Normally, blue bands are useful for water application and distinction between deciduous and coniferous forest. Green band is used for reflectance peak of vegetation, SSS plant vigor, and reflectance from turbid water. Red band operates in the chlorophyll absorption region and is best for detection of roads and bare soil. Near infrared band is useful for estimating biomass, and it separates water bodies from vegetation. Because you know that water reflects very less in visible region and it absorbs almost most of the energy in your infrared region. This particular fifth band, mid-infrared band, is considered to be a best overall band, which separates and which gives most of the surface features information. Coming to the longer short-wave infrared band or mid-infrared band, this band is useful for discriminating mineral and rock. So here you can see this is your green band. Green band is able to highlight urban features more. But when we use the near infrared band, you can see the vegetation and water boundaries are clearly. Now coming to cloud and snow, here in this near infrared band, cloud and snow both are appearing white. But if you have to differentiate between these two, we have to use shortwave infrared. Why? Because in this case, you can see that cloud and snow have similar reflectance value in your shorter wavelength. But when we use a longer wavelength, you can see the snow will have absorption, but your cloud will have constant value. So that's why shortwave infrared can differentiate cloud and snow and cloud. Now coming to the band, shortwave infrared band and difference between thermal band. Here there is an active volcano. Molten lava came out of it is not visible in this, but because of high temperature, it is visible in the thermal. Now coming to radiometric resolution. So as I told that digital number is consist of some numbers, that numbers are actually representing the spectral reflectance value received from the Earth side. So this describes the actual information content in the image, and it is also deciding the sensitivity to the magnitude of electromagnetic energy. The radiometric resolution of an imaging system describes its ability to discriminate very slight differences in energy. How? You can simply see if you have two objects, black and white, you can assign two different black and white color. But when you have multiple shades, and if you assign only black and white, all the features will appear in the similar color. So when you have high radiometric resolution, you can assign different gray labels to the different responses. So finer the radiometric resolution of the sensor, more sensitive it is to detect small differences in reflected or emitted energy. So here you can see this is your 2 to the power number of bits. So one bit is your 0 to 1 gray labels, 2 gray labels are there, 0 being the darkest and 1 being the brightest. With 4 bit you can see 16 gray labels, 0 to dark to bright, dark to bright, and here you can see how the colors of the grayscale is varying. So this is the quick bud image of different gray labels, 2-bit, 3-bit, 4-bit, 5-bit, 6-bit, and 8-bit. So 2-bit means 4 gray labels. So you can see how the 4 gray labels are. And when you have 8-bit, what is the difference between 8-bit and 4-bit? 2-bit data. Now, you can see with this example, this is a cloud shadow present in this first image. And this image is actually having 8-bit radiometric resolution. Actually, the capability of the data is with 11-bit. So when only 8-bit is being used, we are not able to see the features beneath the shadow. But when the data is fully utilized after enhancing it to 11-bit, we can see the features which were beneath the shadow, which were appearing down. Now coming to the temporal resolution, this represents the frequency with which a satellite can revisit an area. It depends upon the instrument's field of vision and satellite size. So application demand is what? Meteorological application, hourly need to monitor the clouds. Oceanographic applications, 2 to 3 days of repetitivity. Stereo viewing, 0 to 1 days of repetitivity. And vegetation monitoring, 5 days of repetitivity. So here you can see, observe the changes. This is the data acquired during November. This is the data acquired during the February. So when the vegetation is in the healthy condition, you can see, and when the autumn came, how the vegetation leaves, when the leaves are shedded, how it is coming in this. Now coming to the various Earth observation satellite. So, various different countries are taking care of the satellite data distribution and all. From Europe, we have Spot series of satellite, and that satellite was actually having off-Nadir look capability. So using that, we can generate even digital elevation model. Spot 6 and 7, this two constellation of satellite was launched in 2012 and 14 with a purpose to provide data, high resolution data till 2024 for entire Earth. Then from Europe, nowadays we have Sentinel-1 and Sentinel-2, which is for microwave, and Sentinel-2 is optical. So they are providing data till 10 meter spatial resolution, which is openly accessible. From Israel, we have IIRS series of satellite. From USA, Landsat series of satellite. Landsat 9 is recently launched in 2021. And commercial satellites are also there, which are providing very high resolution satellite data. Canada is was launching RadarSat series of satellite. From India, we have Indian Remote Sensing Satellite series and Cartosat 2 series. And Japan, we have ALOS satellite. So these are the distribution agencies which are taking care of the satellite data distribution. So from our India, we have National Remote Sensing Center, which is taking care of data distribution. So this is about the Landsat series of satellite. First satellite was launched in 1972 with 185 kilometer swath width and 4 bands, green, red, 2 near infrared band, and 80 meter spatial resolution. First series was 1, 2, 3. Then Landsat 4 was launched in 1983 with thematic mapper, which was having 7 bands, and which included thermal band also with 30 meter resolution. Then Landsat 5 was also with similar specs. Landsat 6 got failed just after the launch, and Landsat 7 was launched in 1999 with additional 15 meter panchromatic mode. Then Landsat 8 was launched in 2013, and Landsat 9 is a kind of continuity mission which was launched on 2021 with operational land imager and thermal infrared sensor, The additional bands were blue, coastal blue band and cirrus band, and thermal bands were two thermal bands were present in this. This is about the Spot series. So as I told, Spot 6 and 7 was launched with a purpose to generate very high resolution wide swath data up to 2024 for entire Earth. Sentinel satellite series, you can see Sentinel 1 is with C band, and this is with dual polarized data. A resolution is 5 meter to 40 meter. And here Sentinel 2 constellation have multispectral imager with varying spatial resolution for varying bands. So for normal blue, green, red, and near infrared band, the spatial resolution is around 10 meter. Then from Japan, ALOS satellite, ALOS 1 was launched in 2006 with a multispectral and panchromatic sensor and microwave sensor. ALOS 2 was launched in 2014 with one of the thermal camera and microwave L-band sensor. This is the, you can say how the remote sensing evolved in your ISRO. So we started with IRS 1A, 1B, with list 1 and list 2 sensors 72 and 36 meter resolution. Now we reached to Cartosat 3 with 25 centimeter resolution in case of Phantom. So we launched also HISIS hyperspectral sensor, then Megatropics, Cartosat series, microwave satellites like RISat 1, 2, and 1A, so 2B. So these satellites are launched from different in different years. So this is the specification of different satellite. IRS 1A, 1B was with list 1 and list 2 sensor with 72 meter and 36 meter resolution with 4 spectral bands, blue, green, red, and near infrared. Then in IRS 1C, 1D, they upgraded the instrument to list 3. Fifth was with wide view, or you can say wide swath acquiring data sensor, and panchromatic is actually with that is a single band sensor. Then resource at 1, 2, and 2A is with AWIPS list 3 and list 4. But the difference is what? Resource at 1 radiometric resolution is lesser than 2 and 2A. Then Cartosat 1 was launched in with panchromatic band with 2.5 meter resolution. Cartosat 2 series, as I was telling, this is with around 0.63 meter resolution in panchromatic. And in case of multispectral, it is 2 meter. And Cartosat 3 with 25 centimeter and 1 meter spatial resolution. So this is about hyperspectral sensors. So in case of our India, ISRO and NASA have collaborated, and NASA's IIRS NG mission was acquired data in various sites in India. HISIS is launched in 2018 by ISRO for defense purpose. And this is RISat 2, RISat 1, and RISat 2B are your microwave satellite sensors. Now you can see the different images acquired from different sensors. So this is your list 1 camera. This is your list 2 camera with 72 meter spatial resolution and 36 meter spatial resolution, how the data sets are appearing. We can interpret some of the features like vegetation, water boundary, some lakes is visible in 36 meter, we can do. Then this is 23 meter. If somebody from Hyderabad, they can identify this is the popular Hussain Sagar Lake surrounded by your Hyderabad city. And this is your panchromatic sensor with panchromatic data of Chandigarh and its surrounding region. Then this is WIP sensor data and AWIP sensor data. This is with 188 meter resolution and this is with 56 meter resolution. So this is from southern part of India. Here you can see the snow. Here you can see the movement of cloud in the sky. This is this 3 image of Hyderabad city again. So with 23 meter even more details started coming into picture. So where older airport of Hyderabad is visible over here, and the building area, the forest, the water bodies are also visible. This is the popular Kankaria Lake area of the Ahmedabad city. And here with the 6 meter resolution, you can identify the different buildings a little better, comparatively better than your 23-meter. This is your Cartosat satellite images from Hyderabad. So here you can see the individual building, the railway station, different vehicles parked in this. That also is visible. This is Vidhan Sabha of Bangalore and the stadium of near to the Vidhan Sabha in Bangalore. And this is some of the Australian airport, how it is appearing in this image. You can see. This is the Cartosat 2 series image, fused image of panchromatic and multispectral. So you can see this is part of Kishangarh city and this is part of Indore city. The Holkar Museum Stadium is visible over here. And here this is Cartosat 3 image of Khalifa Stadium in Doha, Qatar. So here you can see the different vehicles. Color is also clearly visible. Now, Indian ISRO Earth observation missions in the future are ResourceSat 3 and 3A, OceanSat 3 and 3A, RS Sampler 3S and 3SA with 1.25 meters stereo imaging capability. This is the other country's high spatial resolution satellite. ICONOS was the first commercial satellite to provide you the near photographic quality image. Then QuickBird, WorldView 1, 2, 3, and 4, GeoEye creates 1A, 1B. ComSat series is from South Korea. So now I'll be showing it to you the ICONOS image of IIRS campus. How the ICONOS image of IIRS campus is appearing. This is our main building and this is our entire IIRS campus. Okay, here we can have the international hostel. But this image is quite old. Now a lot of changes happen to this particular instrument. This is the Fukushima Daiichi nuclear power plant acquired from GeoEye-1 image of 41 centimeter resolution. And this is the ICONOS image of 2011. So after the disaster, how the building was appearing in this, you can see. Then this is the ComSat 3 and 3A image. So WorldView 3 and 4 is the highest spatial resolution provider from other countries, that is with 31 centimeter data. So here you can see the individual colors of the individual cars with different colors are also visible. In this also you can see with the data, and this ComSat 3 and 3A is also quite available with good spatial resolution, so you can see the detailed features. Now coming to meteorological satellite, this designed specifically for weather prediction and monitoring. Advantages of global coverage at very high temporal resolution. Various types of meteosats are there. NOAA series satellite, GOES and GSAT in geostationary platforms are used for this purpose. India has launched GSAT and INSAT series satellite, which are for telecommunication and meteorological. So where to find this information? So, ITC Netherlands has prepared a database for satellite sensors. So whatever satellites are launched, completed its lifetime, stopped working, and which is going to be launched in future. So many of the satellite details are placed in this website. You can visit that. In this website, you can see how to track the real-time tracking of the satellite. You can go through this link and you can see. And these are the website for browsing the satellite data. nrsc.gov.in. In this Bhunidhi is there. So for browsing the data sets acquired from Indian satellites, one is providing you some of the data sets which are openly accessible till 24-meter resolution. Earth Explorer is for downloading Landsat series of satellite data, and other satellite data sets are also available in that. Sci-Hub Copernicus is for downloading your Sentinel-2 satellite, and EOS Earth data is also for different other satellite data now. So thank you very much, everyone.